All right, so today we will be talking about functions. So many of you are familiar with functions from other courses. In fact, all of you are. But today we're going to look at it from the point of view of set theory, so the most general setting for functions. Okay, so all right, so consider two sets A and B. A function f from A to B is an assignment of exactly one element of B to each element of A. So we use this notation here. F of A is equal to B if B is the unique element of B assigned by the function f element A. All right. And we also make use of this notation. So this notation here is what you'll see in your upper level mathematics courses often, because it's in a general setting, right? So, okay, so consider this relationship here. So here, our set A would consist of the names Tessa, John, Robert, Julia, and Mike. And then our set B will consist of the letters A, B, C, D, and F. So this is like an assignment of possible like grade letters on an exam to students. Right? Okay, so the set A in this case is called the domain. Right? Most of you could have probably guessed that. Can any of you guess what the set B is called? Anybody? It's the codomain. So it's not the range, it's the codomain. However, so if we have a domain set A and a codomain set B, we can look at the image of the set A, and that image is going to be called the range. So here, the image of the set A are the elements A, B, C, and F. So that would be called the range of that function f. Okay, so it's the range of f. It's all the possible values in the codomain for which the domain is mapped to. In upper level mathematics courses like maybe modern algebra or real analysis, you'll often see image and not domain. So just keep that in mind that that's image in place of range. So keep that in mind as you take your upper level courses. Okay, so suppose that we have a function from A to B, and we consider some subset of A, call it S, right? So the image of S under the function f is the subset of B that consists of the images of the elements in S. So if we look at this set builder notation here, we say f of S, which is called the image of S, is the set of all t such that there exists an element S in capital S with t equal to f of S. So let's just look at like a picture of this. So if this is our set S consisting of Tessa, John, and Robert, which is a subset of the domain, then we look to their images and we say that A is the image of Tessa, C is the image of John, and B is the image of Robert. So then this subset here would be called the image of S under F. Okay, so that's just some notation and definitions. Okay, so let's move to our first, I guess, like familiar definition. So a function is said to be one-to-one or an injection if and only if f of A equals f of B implies A is equal to B. And this is for all A and B in the domain of F. So an injection is a one-to-one function, or you can say that a function is called injective if it is one-to-one. So in your previous courses, in like maybe college algebra or pre-cal, you would see one-to-one more often than not. But as you go to your higher level courses, you're going to run into the terminology injection and injective. So always, it's going to be more common that this is the terminology that you'll use in place of one-to-one. Okay, so let's look at an example of this. So here we have our domain and we have our codomain, and we can see that every, so if f of a is equal to f of b, that implies a is equal to b. That's the same thing as saying that everything in the image of the domain has exactly one element that's been mapped to it, right? If you look at these points here, you'll see that no points in here have two pre-images. Each image has exactly one pre-image. Now that's another way of thinking about injective functions. Each image has exactly one pre-image. Okay, so consider this function f from the real numbers to the real numbers defined by f of x equals x plus 2. So I claim that this function is injective. So how do we prove that? Well, let's go back to the definition. F of a equals f of b implies a equals to b. So that's all we need to do. So suppose that we have that the image of a and the image of b are equal, right? So again, like keep in mind, I'm saying image over and over again. I'm just saying that the value of f of a is equal to the value of f of b. Okay, so under that assumption, and by the way that f is defined, we see that a plus 2 must equal b plus 2, right? Because the image of a is a plus 2 under this definition. And the image of b under this definition is b plus 2. So if these two things equal, then these two quantities must equal. And these are real valued quantities, so we can indeed write that equal sign there. So then subtracting 2 on both sides, we get that, oh, a must be the same thing as b. So if we think back to the definition, we've shown it to be true, right? We chose arbitrary images to be equal, and then under the definition of the function, it must follow or it implies that a is equal to b. So we've shown that definition to be valid, so we're done. This is an injective function. All right, so let's look at another definition now. So a function f whose domain and codomain are subsets of the real numbers. So it's called increasing if f of x less than or equal to f of y whenever x is less than y. And strictly increasing when f of x less than f of y whenever x is less than y. In a similar fashion, we can have decreasing and strictly decreasing functions when the inequality here is flipped, right? Okay, so let's look at an example involving a proof now. So I claim that the function from the positive real numbers to the positive real numbers defined by f of x squared, f of x equal to x squared is strictly increasing. Now note that if you look at if you think of the graph of this thing, it's a parabola, right? And parabolas are not strictly increasing, but notice the restricted domain here, right? The domain is only positive real numbers, right? So f of x equals to x squared on only the positive real numbers, just think of the right-hand side of this parabola, that is indeed strictly increasing. All right, so let x and y be positive real numbers and suppose x is less than y. Okay, we need to show that this is strictly increasing, i.e. we need to show that f of x is strictly less than f of y. Okay. So multiplying both sides of this inequality by x gives us x squared less than xy. And note that since these are positive real numbers, that the inequality doesn't flip. That's why I'm able to write this. And then also, multiplying both sides of this inequality by y gives us xy strictly less than y squared. Now, again, the inequality didn't flip because y is a positive real number, so you multiply both sides of this by a positive real number, the inequality doesn't switch signs, right? Okay, together these observations give that f of x equals to x squared, right there, is strictly less than x times y, right? But then x times y is strictly less than y squared, and y squared is equal to f of y. So under the supposition that x is strictly less than y, we see that f of x is strictly less than f of y. So we've shown this function to satisfy the definition of being strictly increasing. We put our QED box, we're done. Okay. All right, so another definition that you're familiar with. A function f from a to b is called onto, or a surjection, if and only if for every element in B, there is an element in A that is mapped to B, right? So basically every element in B has a pre-image in A. That's another way of saying this. So write that down maybe. Every element in B has a pre-image in A, okay? So a function f that is a surjection is called surjective. So again, I'm emphasizing that onto is what you're probably used to from college algebra and pre-cal, but as you go further in your mathematics courses, you're going to see in place of that surjection and surjective as ways to describe these types of functions or property or functions that satisfy this property. So let's look at an example. So here, here's our codomain, and notice that everything in the codomain has a pre-image that exists in the domain. And so everything in the codomain has been mapped to by something, right? Okay, moving on. All right, so let's take a look at these mappings here, or functions. And can we decide which of these is a surjection, which of these is an injection? Are there any of these functions that are both surjective and injective? So take a moment to look at them and see if you can guess the labels for these. Okay, so let's look at the labels. Okay, using one-to-one and onto, or surjective and injective, or injective but not surjective. You get what I'm saying. All right, so this one is injective, right? Everything in the codomain, no, everything in the image of the domain has exactly one pre-image, right? You see that. Okay. This here is surjective because everything in the codomain has a pre-image in the domain. This is surjective and injective, which is another way of saying a bijection, a bijective function, if it satisfies both. So this is a bijection. It satisfies both being injective and surjective. And this is neither, right? It's not injective because the element 2 has two preimages, and it's not surjective because the element 4 has no preimage in the domain. And this is not a function. And why is this not a function? Take a look at it. Any guesses as to why that's not a function? It's not a function because D, right here, the element D in the domain is mapped to two different things in the codomain. And in this is like the set A, this is the set B. D should be only mapped to exactly one thing in the set B, but it's not. It has two images in the set B, so that would not be a function. Okay, so consider the function f from A to B, and it's a injective function. It's a one-to-one function. The inverse function of f, written f with a superscript -1, is the function that assigns to an element b in the codomain the unique element a, such that f of a is equal to f of a is equal to b. Now, f inverse is defined as, using this notation, f inverse of b equals a whenever a is equal to b. Okay. So this definition just means that it's a function that takes the image. So if you look here, the image of a is b, right? So this takes the image of a back to a. Okay, the image of a gets sent back to itself. All right. So let's look at this problem here. Suppose we have a function f from the integers to the integers, defined by f of x equals to x plus 1. Show that f is invertible and find its inverse. Now, in order to find the inverse, it needs to be invertible. So is that function invertible? Or in order to find an inverse, it needs to be an injective function, right? So a one-to-one function. So previously, we showed that f of x equals to x plus 2 was a injective function. And this is just a different constant of 1. So this is injective, so it satisfies being one-to-one. So we can now try to find this inverse of f. So let's do that. So I'm going to do this one on the board. So we can kind of write out the steps. So find f inverse for f of x equals to x plus 1. Okay. So just like note that f of b equals a whenever f of a equals b. F inverse of b equals a whenever f of a equals b, whenever f of a is equal to b, is the same as f inverse of f of x equals to x. So this is the image, right? You think back to the definition of the image, right? So the image of x is equal to x. So the image of a is equal to a. This is just another way of writing it. And also f of f inverse of x also equal to x. Okay. So let's look at the solution here. So what do we want? So we want f inverse of f of x equal x, or f of f inverse of x equal x. We're going to find that inverse function. Okay, so what do we know what f looks like? So f looks like this, right? So another way of writing this is saying maybe something like f, using this part right here, f of f inverse of x equal x, right? But what is f, right? F is the input plus 1, right? Input plus 1. So this is the input, right? So this will be the input plus 1 equals to x, right? So then rearranging, right, we get that the inverse function is equal to x minus 1. Okay? And then this should be it. So this should be it, and we can check, right? So let's just go with the A's and the B's up here and see if it works out. Suppose f of A is equal to B, right? Then, well, I guess like the easiest way to do it would maybe be just to show that this actually works out, right? So f inverse of f of x, and this is, by the way, using composition of functions, is the same thing as saying the input minus 1, right? But f of x is equal to x plus 1, and that's all equal to x. So that was indeed the inverse of the function. Okay? Okay. So one moment. Oh, wrong thing. Okay, so let's continue on with a special type of function. I'm going to share my screen with you again. Okay. So some special types of functions are called sequences. Okay, so a sequence is a function, which a lot of people forget, but sequences are functions. A sequence is a function from a subset of the integers to a set S. we will typically use the notation a lowercase letter subscript n to denote the image of the integer n, right? So notice if this was normal function notation, it'd be like a of n, right? So you read this a of n, like the input is n and a of n is the output or the image of n, okay? So this is the definition of a sequence. So let's look at an example. So consider the sequence defined by a sub n equal to 1 over n. So if we list the terms in this sequence, a sub 1 is going to be 1 over 1, 1. A sub 2 is going to be 1 over 2. A sub 3, 1/3, so forth and so on. So this is a sequence. And these are the images of this sequence. Now, in your upper level mathematics courses, you will often be concerned with bounding the smallest and largest images of a sequence. Notice that this sequence here is strictly decreasing by the definition of the strictly decreasing function, right? Whenever x is strictly less than y, the image of x is strictly greater than the image of y. So this is a strictly decreasing function. And where is it going? What is the smallest value going to be bounded by? And that's a topic that you would see in maybe a Calculus 2 course or a beginning real analysis course. All right, so let's look at a special type of sequence. So a geometric progression is a sequence of the form AR squared, AR to the power n. Now here, A is called the initial term of the sequence, and R is called the common ratio of the sequence, okay? And these are both real numbers. And you can think of R also being next to A here, but the power is 0. So R to the power of 0 is 1 times A, R to the power of 1 times A, R to the power of 2 times A, all the way down, so forth and so on. Okay? So let's look at an example. So the sequence Bn is defined by -1 to the power n. Cn is defined by 2 times 5 to the power n. And Dn is 6 times 1/3 to the power n. These are all geometric sequences. Okay. So the common ratio for Bn is -1. The common ratio for Cn is 5. The common ratio for Dn is 1/3. The initial term for Bn is 1. The initial term for Cn is 2. And the initial term for Dn is 6. Okay, another type of progression. An arithmetic progression is a sequence of the form multiples of some common difference, basically. So we have a plus 0 times d, a plus 1 times d, a plus 2 times d, so forth and so on, where the initial term is a and the common difference is d, and they're both real numbers. So let's look at some examples. So in sequence Sn with initial term -1 and common difference 4, the sequence Tn with initial term 7 and common difference -3. Okay. Okay, so those are some important sequences that we'll run into. Next, let's look at a recurrence relation. So these types of relations happen quite a bit in computer science and are nice ways to write out algorithms to produce a given output. And I'll go over that more a little bit next time. But for now, just know that a recurrence relation is a sequence a sub n that can express a term a sub n in terms of one or more of the previous terms in the sequence. So it's a way of building a sequence based off of pieces of the sequence that you already know. And when this is done, this is said to recursively define the sequence. And all of you are math majors or something very closely related should probably be familiar with this thing called the Fibonacci sequence. Okay, so Fibonacci sequence is defined by initial conditions f naught equal to 0, f1 is equal to 1, and then the rest of this sequence is defined by this recurrence relation. So f sub n is equal to the sum of the previous two images. So the new image is equal to the sum of the previous two whenever we're looking at n greater than or equal to 2. So if we want to define f sub 2, well, that's equal to f sub 1 plus f naught, which is 1 plus 0. Those are already defined, so that's 1. F sub 3 is equal to f sub 2 plus f sub 1, so the sum of the previous two terms, so 1 plus 1. F sub 4 is the sum of the previous two terms, so 2 plus 1 is 3. F sub 5 is the sum of the previous two terms, so forth and so on. And this goes on forever. Okay, so consider the sequence defined by n factorial. So recall that n factorial is n times n minus 1 times n minus 2 times dot 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 times 2 times 1. Right? Suppose a sub 1 is equal to 1. So we define this initial term and we're going to generate this sequence. A sub 2 is 2 times a sub 1, which is 2 times 1. A sub 3 is 3 times the previous term. A sub 4 is 4 times the previous term. And we see that what's really happening is the previous term is the multiples of the numbers prior to it, right? So 4 times a sub 3 is really 4 times 3 times 2 times 1, right? Okay. So next, let's look at how we can produce a sequence. So suppose the sequence is 1, 3, 5, 7, 9. Okay, so notice that the difference between the consecutive terms, so the difference of 2, a difference of 2, a difference of 2, a difference of 2. Right, so we're just adding to get to the next one by 2. So one way of doing this would be to find this recursively and say that the first term in the sequence is 1, and then after that it's the previous term plus 2, right? Because that's just the common difference here between these two terms. But also, we can define this arithmetic sequence, right? Where the common difference is 2 times n, the initial term is 1. So we see that there's often a way to define a sequence in terms of a closed form, like here, or in terms of a recursive form here. And this will happen with many different types of sequences that you'll encounter. Okay. So those are the main aspects of sequences, which are a special type of function. So what have we done today? We've looked at the formal definition of functions. We know what injective and surjective means now. We can prove functions to be injective or surjective. We can prove functions to be increasing or decreasing. And then we can also recognize certain types of sequences and then try to derive a closed form or a recursive form for those sequences. Okay, so that will be it for today. Next time, we're going to look at summations of sequences. So some summations are defined in terms of sequences. And then we'll also look at cardinality of sets. So it should be at least somewhat interesting next time. And that will be it for today. So again, just to remind you, your first exam is due Thursday. Please note the instructions in the title of the email. The title should read your name, Math 2409, fall 2020. Okay. All right, so that'll be it. I'll post this lecture to Blackboard, or no, to my YouTube channel as soon as it finishes rendering. And everyone stay safe, and I'll see you Thursday.